Hi everyone, my name is Chen Wen. I am a PhD student in Shenzhen University in China. Recently, we proposed a novel approach, controlled concurrency testing, via periodical scheduling. So, let's talk about concurrency testing. Controlled concurrency testing is a technique for testing concurrent programs. It controls the order in which threads get executed and explore the space of possible interleaving to detect bugs. There is a good number of existing works. They can be divided into systematic testing and non-systematic testing. By controlling scheduling decisions in either a systematic or non-systematic way, they can reliably explore the schedule space. Despite of their researches, limitations and challenges remain for state-of-the-art controlled concurrency testing in terms of controlled scheduling and schedule space exploration. Many different ways to achieve controlled scheduling are used in existing works. Some approaches require serializing a concurrent program or injecting sleeping delay to interfere with the thread interleaving. They will introduce high overhead, making fewer interleaving can be tested in a limited time. Real-world programs use a plethora of synchronization primitives. Preempted ways could have pathological interaction with the synchronization operation in the target program, leading to false deadlock. Another key challenge is how to effectively explore the schedule space. Exhaustively enumerating all possible thread interleaving is often practically infeasible. The number of thread interleaving grows exponentially with the number of threads and the length of program execution. Randomized techniques only provide probability guarantee of finding bugs. Systematic technique tends to go through a larger schedule space than needed, requiring more overhead or missing some bugs. Therefore, we still need an effective way to explore the schedule space. So, we propose a novel systematic controlled concurrency testing technique called Period. It achieves better control scheduling through an efficient and non-preempted way, and it achieves more effective schedule exploration by using 4 key techniques. Let's take a quick look at the workflow of Period, which contains 3 main components: schedule generator, periodical executor, and feedback analyzer. Given the source code, Period first applies static analysis to identify key points. Key points are statements that are key to the program observable behavior, such as the statement accessing shared memory location or synchronization primitives. The schedule generator generates schedule according to the number of key points. A schedule is a series of execution phases that contains thread identifiers. The schedule generator imports a schedule bounding technique to systematically generate schedules that are likely to incur bugs. The periodical executor uses a series of periods to host the execution. It enforces the generated schedule in the execution. The feedback analyzer makes use of runtime information, such as key points, dynamic key point slice, and schedule prefix to guide the schedule generator to effectively generate legal schedule. Next, I will show you how Period works through a running example simplified from a real-world CVE. 2 threads concurrently invoke the function once, and are synchronized with the help of 3 variables: lock, waiters, and down. The variable lock, allocated in the main thread and released in the child thread, is used to protect the critical section. The variable waiters indicate the number of threads waiting to enter the critical section. The variable down will be set to 1 once the critical section is complete, and other thread created later may return directly. The expected behavior is that only the last thread should release the lock and should not incur a use-after-free or double-free bug. Traditional testing does not explicitly control the thread schedule. Therefore, such testing often ends up executing the same thread interleaving many times and difficult to find concurrency bugs. In our approach, static analysis is used to identify key points. All the statements that access shared memory location or contains synchronization primitives are identified as key points, so that we can find 9 key points in function once. We will explore the schedule space gradually. We first only schedule the first key point of each thread and try to make one thread execute after another thread complete. After running across 2 schedules with 2 periods, we found that more key points are covered. We further consider this key point as a dynamic key point slice. Based on the newly obtained dynamic slice, we continue to systematically generate schedule with an increasing number of periods. Among these 8 schedules, a new dynamic key point slice and a non-pointer dereference box are found. We will carry on schedule exploration based on this dynamic key point slice with a fixed schedule prefix, as the schedule prefix contains necessary context switches to reach this dynamic slice. It can be used to guide the further schedule exploration. We will find another new dynamic key point slice, which makes both 2 threads have a chance to free the lock. Based on this dynamic key point slice and a fixed schedule prefix, we can find the use-after-free and double-free bugs. Finally, we start the exploration when all the obtained dynamic key point slices are explored within the preset period number bound. In addition, we design a parascheduler. The parascheduler allows the isolation of a specific order on field statement while letting the rest of the program execute concurrently. This optimization makes it possible to reduce the schedule space to explore when there are many working threads. We have performed a thorough evaluation. This is the experimental result on CVE benchmark, including 10 real-world CVEs. For comparison, we have selected 6 well-known and representative controlled concurrency testing techniques, 2 recent work that use predictive analysis, and also 3 race detectors. The results show that Period successfully identify more bugs than other competitors. Here is the first half of the table, showing the experimental result on SCT bench. The results include both versions of Period, equipped with our parascheduler and without the parascheduler. With parascheduler, Period explores schedule space more effectively, allowing more bugs to be detected. And here is the second half. The results show that both versions of Period, equipped with our parascheduler and without the parascheduler, outperform other controlled concurrency testing techniques in terms of concurrency bug finding ability. In summary, we present a controlled concurrency testing technique called Period. It achieves better control scheduling and more effective schedule exploration. It outperforms state-of-the-art control concurrency testing technique, and you can try our artifact out from this link. Thank you.